dedicated viewers out there. This is the additional one. So in case you did the one that I gave you yesterday and you finished and you checked the video today in class and you did it right and you just want something extra, this is that something extra. All right, so question 1 says, the rectangle has side lengths r and s for each expression, say whether it gives the perimeter of the rectangle or the area of the rectangle or neither. So there is here, let's call it length and width. So this is the length and this is the width, and the width is r and the length is s. Now, you know what? If you don't like those letters, give them numbers. Let's pretend that's 4. Let's pretend this is 5. That's fine too. I won't tell anyone. So, A, what happens if I add R and S? And just R and S. What happens if I add 4 plus 5? It gives me 9. So is that the perimeter of the rectangle? No. Is that the area of the rectangle? No. So this one, in letter A, it's neither. It's just adding this dimension, this length here, and this length. Not all of it, just this one and this one. Okay. Second one, r times s. What happens if I take r, which is represented by the number 4, and I take s, which is represented by 5, and I multiply them? 4 times 5 gives you 20. What does that actually represent to 20? If you multiply 4 and 5 is, you get the area, the number of square units inside. So 1, 2, 3, 4, 5, and then coming across. So it's a shortcut, right? If I multiply 4 and 5, I get 20, which is the number of square units, and that's what happens when I multiply r, whatever number it is, with s, whatever number that is. Okay. Oops. Again, I chose 4 and 5. You could have picked 5 and 7, 3 and 5, 3 and 4. It doesn't matter. I picked 2 numbers. Now what happens here? What happens if I multiply r, which is represented by 4, times 2? Then I multiply 2 times s, which is represented by 5, and then add their sums. What does that give me? Well, 2 times r. So that means 2 times 4 plus, and then s here, which is represented by 5, I'm going to multiply. I get 2 times 4, which is 8. 2 times 5, which is 10. I get 18. And what did I just do? I actually found the perimeter. Right, think about it. If you were going to take, and this is a park around your house, and you take your dog for a walk, you would walk 5 units this way. So let me write 5. You walk 4 units up, so another 4 units. And you would walk 5 going left, another 5. And you would walk 4 down. All right, so that's the total distance you walked. 5 plus 4 plus 5 plus 4, which is 18. So literally you multiply 2 times 4, 2 times 5, which is the same thing as 5 plus 5. And then you did 2 times 4, which is the same thing as 4 plus 4. Right, multiplication is repeated addition. So we got 18. Right, so here's the 5 and the 4. So 2 times r plus 2 times s. If you were to do that, you're actually finding the perimeter of this particular shape. Next one. What if you took r, which we said was 4, and you took s, which we said was 5, raised it to the second power? So let's replace r with 4, raise it to the second power. Let's take s, which is 5, raise it to the second power. Do you think we're going to get the perimeter? Well, 4 to the second power is actually 4 times 4. Plus, and 5 to the second power is actually 5 times 4. 4 times 4 is 16. 5 times 5 is 25. And if you combine those, you get 41. Is that the area of our shape? No, because we already know the area was 20. Is that the perimeter of this particular shape? Right, the distance around the shape? No, we already found this 18. So what's 41? It's neither. So taking one of the sides, raising it to second power, plus raising the other side, raising it to second power, and adding them both gets you neither. Doesn't get you the area nor the perimeter. Here's a polygon. Draw a scale copy of the polygon with a scale factor of 3. So again, if we're going to do a scale factor, right? So I I know a couple of things before I even start. The image that I'm about to create is going to be the same type of image, but just where the dimensions, right? These sides here are all going to be bigger by a scale of factor of 3. So let's see what that means. If I were you, for these, I'm going to do these two because it's straight lines and we can count. 2 and this is 4. So let's just do these two because the other ones are diagonals. Okay, I'll explain why it's a little bit harder for those in a second. So scale factor of 3, which means instead of 4, we can multiply every side, even these that I didn't write, every dimension that I have times 3. I'll put in parentheses. So 2 times 3 is 6, so that height there, that's 2 is now 6. So 1, 2, 3, 4, 5, 6. This one, 1, 2, 3, 4, so now it's 4 times 3 becomes 12. So 2, 4, 6, 8, 10, 12. It goes over here. How am I going to do that? So this is going to go, so if you look at this, right, this distance, I'm going to repeat that distance, which goes through, it's a diagonal. Right, go through the diagonal of 3 squares, so we're going to go here, that distance. Right, so let me copy that once. Once. We're going to repeat that again twice, and repeat that same thing 3 times. Right, so. And that, you have to go through you have to count that, the diagonals. And then once that's done, the last two, much easier to connect. So this would be the scale copy as a factor of 3. What is this? Jada drank 2 liters of water. So this one is actually a nice little poem. Simple, but it talks about what happens, right, when the scale factor is greater than 1, less than 1, equal to 1, but in terms of drinking water. So let's write that Jada drank 2 liters of water. I'm going to actually take this guy here and move it. Right, 2 liters of water. And change colors. And then Andre drank, oh no. Well, I think this one here, I remember, it's supposed to be 3/4, and Lee drank 3/4 times as much as water there, and Lynn drank 3 times. Okay, so this one, the number that's missing is 3/4. So Andre drank 3/4 as much water as Jada. So think about that. So here's what Jada, so you're gonna take whatever Jada drank and multiply that by 3/4. Now this guy right here, think about scale factor. If you multiply by a number equal to 1, it stays the same. Multiply by a number greater than 1, right? It's going to be greater. And if you multiply it by a number less than 1, it's going to, your product is going to be smaller. So think about this. This is what Jada drank. Jada drank times 3/4 of that. So is whatever Andre drank more than Jada or less than Jada? You know, if we multiply this, what do we get? 2 times 3 is 6. Again, you can put this over 1. 2 times 3 is 6. 1 times 4 is 4. If you simplify this, it becomes 3/2 or 1.5, 1.5, however you want to look at it. Okay? So it's 1.5 less than Jada or more than Jada. So did Andre drink less or more than Jada? Well, he drank less because when we multiplied what Jada drank, he drank less because when we multiply what Jada drank by a factor less than 1, less than 1, we knew, or I knew, his amount would be less than whatever Jada drank. Okay, so 2 times 3/4, is it going to be greater than 2, equal to 2, or less than 2? And in this case, because 3/4 is a number less than 1, look, it ended up being 1.5. So let's talk about, what's his name? Lynn. I'll do Lynn here in the box. So Lynn drank 3 times as much as Jada. So here's what Jada drank. We can multiply to find out how much Lynn drank. We gotta multiply by 3. Take a look at this number. Think scale factor here, right? So if I multiply what the original amount, which was 2 times 3, and then 3 is a number greater than 1. So whatever Lynn drank, is it gonna be greater than Jada, less than Jada, or equal to Jada? Well, because it's greater than 1, the number is going to be greater. So obviously 6 liters. All right, and you can write that same explanation. Each small square in the bracket represents 1 square unit. Find the area. Okay, so how can we find? Think about decomposing this, right, into shapes that you are familiar with. So if you don't know the area of a trapezoid, right, you don't know the formula for the area of a trapezoid, you don't even need it. So let's divide this first shape into 2 shapes that I'm familiar with. There's a square and there's a triangle. Now, even a triangle, some of you might not remember the area of a triangle, and that's fine. Let me do this. So before I even start this, let's look at this for a second. If I asked you to find the area of this rectangle, you'd say that's easy. That's 2 units, this is 3 units. We can just multiply 2 by 3, or we can even count 1, 2, 3, 4, 5, 6. So the area would be 6 square units. But what happens if I take that rectangle and cut it in half? Just like that. If I cut it in half just like that, and I asked you now, well, what's the area here of this guy here? Well, if the original area was 6 and you cut it by half, that means that the green area here would be 3, right? Because it's half of the 6 that was a rectangle. So think of that as a means to find the area of a triangle. It's pretend, so you can make a triangle. So let's say you had this triangle. Let's say this was, I don't know, 5 and this was 3, right? You can complete the triangle so that the triangle is now a rectangle. Pretend it's a rectangle. Multiply 5 and 3, you get 15, but because we only have half of the rectangle, right? Think about half of the rectangle. Divide that by 2, the area would be 7.5. Just another way of, in case you forget the area, the formula for the area of a triangle. Right? Think about it that way. So here, the square has 1, 2, 3, 4, 5, 6, 7, 8, 9. So this, right? Because this measures 3. So you could have said, oh, I can just multiply 3. 3, it's a rectangle, it's a square. So inside here, so area of the square is 9 square units. What about the triangle? Well, take that triangle. I mean, what if it was a rectangle? Well, if it was a rectangle, I'll put a dot here. If it was a rectangle, this is 1, right? The unit. This length right here is 1 and the height is 3. Well, if it was a rectangle, it would be 1 times 3, which is 3. But it's not a rectangle, it's half a rectangle. So take the 3, right? So for the triangle, you're going to multiply the 1, right? The length here, times the height, which is 3. And then you're going to divide that in by 2. 1 times 3 is 3. Divided by 2, you get 1.5. So the area of that triangle is 1.5 square units. But that still doesn't answer our question. Our question is, what's the total area? Well, the total area of this shape is the 9 that was inside the square and the 1.5 that was in the triangle. So 9 plus 1.5, so the area of this composite figure is 10.5 square units. Here, oh my God, what can we do here? Again, whatever you're familiar and comfortable with. I'm gonna break this down into some shapes. I'll break it down into one big rectangle here. I'll break it down into a triangle. Hopefully you can see the triangle. There's a triangle there. And there's two other triangles. One right here and one right here. And then I can just add them up, add them all up and find the area. So let me do rectangle here. Let me show you a better color. Here, rectangle. The rectangle here is 1, 2, 3, 4. Going up is 1, 2, 3. We can just do 4 times 3 and we get 12. So this triangle over here, now the long here, this guy here. All right, so going the length here is just 1, and if you count the height, it's 1, 2, 3, 4, and goes all the way to the top, making that 5. Now, how do you remember the area of a triangle? Well, if you think about it, if it was a rectangle, I'll just pretend it was a rectangle, it would be 1 times 5, which is 5. So if it was a rectangle, it would be 1 times 5, and the answer would be 5. But it's not a rectangle, it's half of a rectangle, so we have to divide it by 2. So this area here is 2.5. Now let's take this guy here. Okay. Same exact thing. So you can even see if I actually made a rectangle. That would be the rectangle. Or in this case, a square. So I take this guy. Right, looks like this. So it looks like this. This is 2, and this is 2, right? So again, if you think of it as, in this case, a square, 2 times 2 would be 4. And you can see, look, 1, 2, 3, 4. If that was a square, the area would be 4. So 2 times 2. But because we only want half of it, we got divided by 2. So 2 times 2 is 4, divided by 2 gives me 2. And then on the other side, we had this right here, purple triangle, which again, we can think of it as a square, right? We'll think of it as a square. It repeats the same pattern here. Here's what I had. This was 2 and this was 2. So if you think of it as a square, you had 1, 2, 3, 4 square units, but because it's half of it, you have to divide it by 2. So it's 2 times 2 for the area of the square, but we only want half of it. Divide by 2 again, you get 2. What I do now, I have to take this guy, this guy, this guy, this guy, and add them all up. So 2, 4 plus 2.5 is 6.5. 6.5 plus 12, total area 18. Oof. Oh my God. Draw it out. Let's draw a rectangle here. Okay. There's another strategy. Draw it out. Write it out. So you don't have to imagine things. Right? Have it visually in front of you. So we have a rectangle, and it measures 9 over here, and it measures 3 inches, by the way. Rectangle B is a scaled copy, so we made a scaled copy. So if it's a scaled copy, we know it's going to be the same as the rectangle as well. Right? And whatever scale factor we use to reduce or make a larger scaled copy was the same. Select all the measurement pairs that could be the dimensions of the rectangle. So I don't know. Somebody made a scaled copy, and I don't know if they made it big or small. Let's do the first one. 4.5 by 1.5. So this will be 4.5. This will be 1.5. So 3. I mean, if you want to think about is this guy here a scale copy of? So this is the original. So let me write the original here. So let's talk about copy. So does this copy work? Copy A. Does 1.5. How do I get from 1.5 to 3? Well, times 2. How do I get 4.5 to 9 times 2? So scale factor, going bigger is 2, and then the scale factor, if I went this way, right, reduction, if I multiply 9 times, what's the reciprocal of 2? 5.5. So 9 times a half, is it 4.5? Yes. 3 times a half, is it 1.5? Yes. So does 8 work? Yes, it does. Let's look at B. 8 inches by 8 does. That is 4.5. This is 1.5. So somebody made a bigger one. This is 8. And this is 2. sorry. That's not it. The original was actually 9 by 3. This is 9. And this is 3. All right. So you have to determine right, this is the original one. It's not the scale, so somebody made a rectangle and said, hey, this is 8 and this is 2. Well, you can look at it going this way or going that way, whichever one, it doesn't really matter. But is this copy a scale copy? Well, does it look like the shape is about the same? Yes. Are we using the same scale factor? Well, let's check. How does a 2 become a 3, or how does a 3 become a 2? Right, so the 2 to become a 3 is times 1.5. 2 times 1.5, 2 times $1.50 is 3. Now, 8, if I take 8 and multiply by 1.5, will I get 9? No, I won't. Okay, I'll get 12. So, is copy B a scaled copy? No, it's not. This one is garbage. C, you know, 10 by what? By 4. Okay, so this is now 10. Let's copy C. And this is 4. Well, what's another way of doing this? Well, like I said, you can find the scale factor, right? But you can also here, because it's a rectangle, we can also use proportion. We can use corresponding sides. So in this here, in the original, we can say the ratio of these two sides should be equal to the ratio of the corresponding side. So on this rectangle, 3 matches with who on the copy rectangle? Well, the corresponding side would be this guy, which is now 4. So 4 should have the same ratio as 3 to 9, and then again 9 represents the length here, so I'm going to use the length of the second rectangle. So 3 to 9, the ratio of 3 to 9 is the same thing as the ratio of 4 to 10. Is it? Well, that's one way we can quickly decide if these two ratios are equal. We can cross multiply and see that it's not, right? And the other thing, we can simplify 3 over 9 and write 1 over 3. We can simplify 4 over 10 and write 2 over 5. And are those two ratios the same? They are not. So right off the bat, we know that this guy also is not in our good graces. 13.5, so somebody made a triangle, and this is 13.5, you know. 13.5, and this is 4.5. So again, we can use, I probably would use, so that I don't have to find scale factor, I can use a proportion. So in the original, set up a ratio. The ratio of this, the height, and the length, which is 9, is the same as the ratio, this is the copy, of the height, which is 4.5, over the length, which is 13.5. So notice, and I forgot to, I didn't write it, so this is the height, right, and this is on the other side, it's also the height, and at the bottom, this is the length, and this is the length. So the ratio of the two sides in the original triangle has to match the corresponding ratio of the two corresponding sides. So let's cross multiply. Or not. Un momento.
So I multiply, what is that number? 13.5. 3 times 13.5, I get 40.5. So I multiply these two, I get 40.5. 9 times 4.5 equals 40.5. Look at that. So D is a scaled copy. Okay. If you wanted to find a scale copy, you could. Does anybody remember how? Well, let's go scale copy this way. What was a scale copy? What do we multiply from the original to get to the copy? Well, the scale factor. It's getting bigger, so we can use big over small. Let's pick two corresponding sides. Let's use this guy and this guy. So it'll be 4.5 over 3. And then 4.5 over 3 is the same thing as 1.5. So the scale factor for the original to become the copy was 1.5. So if I multiply 3 times 1.5, will I get 4.5? I do. If I multiply 9 times 1.5, will I get 13.5? Yes, I do. So we can use a proportion, and we can find the scale factor. Last one of this, of 5. Not the last one. So somebody made it even bigger. This one's a little bit easier. This is 90 inches. This is 30 inches. This is definitely a scale copy. What's a scale factor? We can, you have to do anything. It's times 10. What's a scale factor here? Times 10. So if all the dimensions on the original shape rectangle get multiplied by a factor of 10. Yes. If you want to set a proportion, so take the two sides of the original. Right? This is the width, and this is the length. And let's see if it's the same ratio as the width on the copy, which is 30, right? That's the width. And then 90 at the bottom, which is the length. Are those two ratios the same? Yeah, 3 over 9 is the same thing as 1/3. 30 over 9 is the same thing as a third. Are those three ratios the same? Yes, they are. So this one is also a scale. I know. No comments. 6. Write the scale down. 4 centimeters, ladies and gentlemen. This represents 5 kilometers in your life. So 4 centimeters in your notebook represents 5 kilometers in your life. You want to simplify that? You can. Let's see if we need to. What distance on the map in centimeters represents an actual distance of 4 kilometers? So 4 kilometers. We can use a proportion, right? So x centimeters. So 4 kilometers. What would that be in your notebook? How many centimeters would that be? Well, cross multiply. 4 times 4 is 16. 5 times x is 5x. Divide by 5. X equals 5.1. Sorry, did I say 5? 16 divided by 5. Sorry, 3.2. What was it? So in centimeters, 4 kilometers is 3.2 centimeters. What's the actual distance of kilometers that is represented by 5 centimeters? So if you drew 5 centimeters on your notebook, how many kilometers do you represent in real life? Well, you use the scale. So 4 centimeters, 5 kilometers. What if I have 5 centimeters? How many kilometers would that be? Here I'm going to put x. Cross 4x. 5 and 5 is 25. Divide by 4. Divide by 4. And x equals 25 divided by 4, which is 6.25. So, on a map, it would be 6.25 kilometers. 7. Tyler has 2 different maps of Ohio. Right? The first map has a scale of 1 centimeter to 10 kilometers. Right? Distance from Cincinnati to Ohio is 40 centimeters. The scale on the second map is 1 centimeter to 50 kilometers. Okay. What is the distance from Cleveland to Cincinnati on the second map? Okay. Distance from what? Wait. The distance from Cleveland to Cincinnati is 40 centimeters. Okay. Alright, so using the first scale, let's see if we can solve this. The distance from Cleveland to, okay, so 40 centimeters would be how much in real life? Okay. So put an X, cross multiply. 1 times X is X. So 10 times 40 is 400 kilometers. So in real life, the distance to Cincinnati, from Cleveland to Cincinnati is 400 kilometers, which is about right. So I want to take this information to help me solve the second part, because on the second part, here's what the setup is currently. I wanted to know what is the distance from Cleveland to Cincinnati on this map. Right? So now, just out of curiosity, looking at the scales, this one is 1 centimeter to 10 kilometers. This one is 1 centimeter to 50 kilometers. Is the second scale going to be greater than the first one? Equal to the first one? Or less than the first one? Think about that. It's going to be smaller. The smaller second map is going to be smaller. Why? Because in the same centimeter here, I represent 50. So I don't need a lot of centimeters, right? So I'm going to use less centimeters, which makes the map smaller. So we know that the two cities is 400 kilometers distance range. Right, so using this scale, how much smaller? Well, let's see. Cross multiply 50x equals 400. Divide by 50, divide by 50. X equals 8 centimeters. Okay. So notice the difference. In this map, Cleveland to Cincinnati is 8 centimeters. And in this map, Cleveland to Cincinnati is 40 centimeters. Allie wants to make a scale drawing of her bedroom. The bedroom is a rectangle. Let's draw the bedroom. Which measures 5 and 3 meters. So 5 meters. So that's in real life, 3 meters. Draw. Right, she decides to use a scale 1 centimeter to 50 centimeters. Oh no. Right, so we have a couple of issues. First issue is that your scale is in centimeters, but this is in meters. So we're going to change a few things. So leave that. Instead of saying 3 meters, we're going to say 300 centimeters. Every meter, that's 100 centimeters. And instead of saying 6 meters, we're going to say 600 centimeters. So now our scale can work. So draw and label the dimension of the scale using the scale 1 to 50. So using this. What do we have here? No, not again. Oh, God. Alright, so where was I? It was 5 meters. We have a bedroom, right, which measured 5 meters here, and this was 3 meters. I'm going to change this to centimeters, so this became 300 centimeters, and this became 500 centimeters. So I'm still on question A. Use a scale, so that's in real life, 5 meters. For you to get a reference, I'm about 180, 1 meter and 80 centimeters. So 5 meters is about 3 and a little bit, 0.4. Alright, so using the scale, so if I had a bedroom that measured 5 meters this way and then 3 meters up, how would I draw that in my notebook or my sketchbook? Well, here's my scale. 1 centimeter is 50 centimeters in real life. I have 3. Let's use this side. 300 centimeters. How many centimeters would that be in my notebook? Cross multiply, we get 50x equals 300. Divide by 50, divide by 50. X equals 6. So I'm writing my notebook. This would be 6 centimeters. On the other side, let's figure out what 3 meters is. So 1 centimeter is to 50 centimeters in real life. And then what happens is if the height of my living room is 300 centimeters, how many centimeters will I use to represent that in my notebook? Cross multiply, 50x equals 300, x equals 6. 6 again? No, it can't be. Okay, so, sorry. It's not. Because I used the wrong number, so this is supposed to be 500. I already did the height, so I'm not doing the length. Okay. 500, cross multiply, we got 50x equals 500, divided by 10 on both sides. By like 50 on both sides, and x equals 10. So this guy here, and I did it backwards, this guy here is 6, and this guy here is 10. Right, so that would be in my notebook. Okay. Now this bedroom door is 0.8 meters wide, so the door, what would be on my drawing in my notebook? Again, let's use a scale. 1 centimeter is 50 centimeters. Now 0.8, notice that all my units here are my proportion that I'm about to set is all in centimeters. So I gotta change 0.8 meters. What's 0.8 meters in centimeters? That would be 80 centimeters. So what's 80 centimeters in my notebook? How many centimeters will I use? We'll cross multiply. 50x equals 80, divide by 50, divide by 50, x equals 1 point something. 80 divided by 50, 80 divided by 50, 1.6. So in my drawing my notebook, when I draw that door, or the width of that door, it would be about 1.6 centimeters. Okay. Elena's bed measure, so in my drawing, her bed measures 4 going this way centimeters and 3 centimeters going this way. What is the dimensions of her bed in real life? Again, we get to use this proportion. 1 centimeter is 50 centimeters. One side of her bed is 4 centimeters over x. Plus multiply, and x equals 200 centimeters. So in real life, this side of her bed, the one that says 4, okay, is 200 centimeters. Now the one that says 3, so again, back to my proportion. 1 centimeter represents 50 centimeters, and if we have 3 centimeters, how many centimeters would that be? Cross multiply, and we see that x equals 150. Okay. 5 more. Oh no. Alright, 9. One of those questions again. This, put a star on it, would definitely be there, so let's do that. They're saying that it is a scale copy. So if it's a scale copy, we know all the dimensions. We'll multiply by the same scale factor. Can we figure that out? Well, the only one that we have this guy here. This is 5, and this corresponding side is the same side, right? one that matches the height, it's 10. So what was the scale factor going this way? Seems that everything was multiplied by 10. And therefore, if I go back this way, going smaller, what's the reciprocal of 2? Be 1 or 2. So going the other way, let's fill in some numbers. This side is 8, so on this side would be 4. This side is 4, on this one would be 2. And this side, that's 6, on the scale copy would be 3. Right. Did they ask us to put the letters, the numbers? No. Will it help? I hope so. Let's look at segment BC. Segment BC is this guy here. And it says it's half of the length of EF. EF is 2. BC is, BC is 2 and EF is 6. Is 2 half of 6? No. See ya. CD. Where's CD? CD is here. CD is 4. It's half the length of GH. Where's GH? GH right here. Is 4 half of 8? Yes. That's good. Let me change colors. The measurement of angle ADC. Angle ADC. Where are you? Angle ADC. ADC, which is this angle right here. And is equal to the measurement of angle EHG. Where's EHG? Which is also that one is true. The length of AB is 3 units. Where is AB? Yeah, from here to here we found out it's 3. And the area of ABCD is half the area of EFG. So that's not how it works. Okay. 10. Oh, 2 more. Scale drawing of a park, a rectangular park, is 6 by 5. Okay. So let's make this a 6 and this by 5 inches. The actual park is 240 feet long. So the actual park is 240 feet long. What is the actual area of the parking lot in square feet? So in order to find the actual area, I need, right, this is the area, and they're saying, well, I can't find the area of this shape. Why? Because I'm missing this guy. So let's go ahead and find that one. What's the scale? The scale says 6 inches. No, that's not the scale. Just a measurement. What's the scale? Alright, they don't give us a scale. Let's find the scale. So according to this, it says that's 6 inches, and we can tell, right, just by looking at the picture, this 6 inches is represented by what? Well, it's represented by this guy. I couldn't do 5 inches because I don't have the height. So 6 inches represents, in real life, 240 feet. You want to simplify? You can. You can divide top and bottom by 6. 6 divided by 6 is 1 inch. 240 divided by 6 is 40. So we can use this scale. So you could have used this one, but if you want to, you can use the simplified version. Now, the scale now that we know the scale, we can find out our measurement. So inches on top, feet at the bottom. 1 inch is 40 feet. So what happens if I have 5 inches over here? How many feet is that? So I'll put 5 over here and find out the rest. Cross multiply, x times 1 is x. 40 times 5 is 200. So in real life, this side that I didn't know now is worth 200 feet. Is that a question? No. They are asking us what is the actual area. And to find the area, now that I have all the moving parts, right, this measures 200 feet. Find the area and multiply 240 times 200. And I get some big number. 240 times 200. 48,000 feet square. 48,000 feet square. Or square feet. 11. Oh my God. The Tyler has 2 different maps of Ohio. The scale on the first map is 1 centimeter, 30 kilometers. Okay, I can understand that. It's the same problem as before. the distance from Cleveland to Ohio, to Cincinnati, sorry, Cincinnati is, what is the distance? 420 kilometers. The scale on the second map is 1 centimeter is 60 kilometers. All right, so if we're trying to create a map in our notebook on our sketch, and the distance is, what is the distance? 420 kilometers. Which map will be smaller? A or B? Well, we know it's going to be B because this particular ratio, we have more kilometers represented in 1 centimeter than this one here. This here, 1 centimeter only represents 30 kilometers. So, and this one, 1 centimeter represents 60 kilometers. What does that mean? It means when we draw the distance in our notebooks, right, we don't need as many centimeters to represent 60 kilometers. So let's try that. So let's do both. Let me write equal centimeters, kilometers. So if I wanted to do 420 kilometers, cross multiply, we get 60x equals 420, divide by 60, divide by 60, x equals 7. So using the scale 1 centimeter to 60 kilometers, I only need 7 centimeters. But what about if I use this scale, where it doesn't represent as many miles? So again, centimeters and kilometers. This is going to be 420, this is going to be x. 30x equals 420. Divide by 30, divide by 30. X equals 104. 420 divided by 30. Equals, no, 14. I'm going to get 104. 14. And you can tell what I was talking about before. With a ratio where kilometers are not, with less kilometers represented by the centimeter, and that is going to be, this is going to be bigger. And which one's smaller? Well, if you want to make a smaller map, you definitely have to use the ratio where 1 centimeter represents more kilometers than the other ratio. Okay, I think that's it. Please go through your notes for tomorrow.